In this video, we will discuss circular motion. There are cases where an object moves around in a circle. For instance, the moon orbits the Earth in a circle. Another example, you could easily take a yo-yo and spin it around in a circle. In this lesson, we will discuss the conditions required to make that kind of motion happen. Imagine an object going around in a circle. Let's say it starts here, and then it moves to here, and then here, and finally back to here. At all points traveling in the circle, it maintains a constant distance from the center of the circle, which we call the radius. However, it does move around the arc of the circle. While we normally break velocity into x and y components, when dealing with circular motion, it will be helpful to break up the velocity in a different way. We say that the object has two components of velocity. It has a radial component, which means how much the radius changes per unit of time, and is directed along the path from the center of the circle to the object. If the object is truly traveling in a circle, then the radial velocity has to be 0. Otherwise, its radius is changing, and that would not be a circle. The other component is called the tangential component, and it is always at a 90-degree angle from the radius line. This component tells us how quickly the object moves around the arc of a circle. For instance, if the circle has a radius of r, then we know its circumference, or the distance to go all the way around the circle, equals 2 pi times r. If we wanted to know how long it takes for an object to get around the circle, then we would take this distance of 2 pi times r and divide it by the tangential velocity. This formula tells us how long it takes for the object to make one full revolution around the circle, and it is called the period. For instance, the period of the Earth's motion around the Sun is 365 days, or what we more commonly refer to as a year. Now, an object that has a constant velocity and feels no acceleration will not move in a circle. If we had an object start here with some velocity that is pointed along the tangent of the circle, a short while later it would end up over here. But at that position, the radius is definitely larger than it was before. If the radius increases, then the radial velocity is not 0, and it is not traveling in a circle. So the way it works is like this. The moment that an object is traveling along the tangent of the circle, it has a radial velocity of 0. However, that radial velocity will increase as time passes and the particle continues to move in its straight path. This means that there is a radial acceleration, since the radial velocity changes. That radial acceleration is called a centrifugal acceleration, and it means that the radial velocity will increase outwards. This radial acceleration will always exist, since particles like to move in a straight line, and this is its value. It is the tangential velocity squared divided by the radius of the circle. In order to travel in a circle, we must have an inward radial acceleration of the same magnitude that can cancel the outward centrifugal acceleration. Such an inward acceleration is called a centripetal acceleration. This inward radial acceleration isn't automatic though, and it needs to be created by something. As always, an acceleration is created by a force, according to the equation F equals ma. Therefore, we need a force that is directed inward along the radius that has a magnitude of the mass of the object times the centripetal acceleration required to go in a circle. So we find that the required centripetal force is mv squared over r. By the way, since we are assuming that the radial velocity is 0, we can now just use the speed of the object, v, and its tangential speed, v sub t, interchangeably, since all of its speed is contained in its tangential component. To give an example of this, imagine you swing a yo-yo around your head. If you swing the yo-yo horizontally, what will be the tension in the string? So let's draw the forces involved. Since we are swinging the yo-yo horizontally, we don't need to consider gravity. So the first force to consider is the outward radial force, which is called the centrifugal force. It has a magnitude of the mass times v squared over r. However, this force is trying to stretch the string, and if we remember how tension works, tension kicks in to make sure the string can never be stretched. Therefore, we write that the centrifugal force minus the tension force must equal 0, since the radial acceleration must be 0. This means that tension equals the centrifugal force. Let's summarize. We have learned that we can break a circular motion into a tangential and a radial component. In order for the motion to be circular, the radial velocity and acceleration need to be 0. Since objects move in a straight line unless they feel some acceleration, the radial velocity will not normally remain 0, and will instead accelerate at a rate of v squared over r. Therefore, to make an object move in a circle, it needs to feel an acceleration of the same magnitude in the inward direction to make the overall radial acceleration 0. Finally, we learn that accelerations can be linked to forces, So we can talk about a centrifugal force, which is the force that always pulls the object radially outward. It is not truly a force, but it exists when we consider the radial direction, since an object naturally tends to accelerate radially outward as it travels on a simple line. We also then can have a centripetal force, which is a force that pulls the object radially inward, and is applied to cancel the centrifugal force. This is an actual force that is applied, which is meant to cancel the natural drifting of an object out of a circular path. That is it for this video. Thanks for watching.